Yesterday, I had you watch a video about the misconceptions that people have about temperature. And sometimes just because you touch something doesn't necessarily mean the temperature is different. A lot of that has to do with specific heat capacity and the amount of heat that is readily transferred from one type of substance to another. Some substances just plain take a lot longer to heat up than other substances do. And this is something that you instinctively know whether you are actively aware of it or not. For example, if you put a pot of water on the stove to boil, maybe you're planning to make some pasta for dinner, and you already know that the water inside of that pot is going to take a lot longer to get hot than the pot itself is going to. You know that if you put just an empty pan on the stove, that maybe you're going to melt some butter and fry an egg in or something. You know that that pan is going to get hot a lot faster than a pan of water is going to get hot. And the reason for that is because of a specific heat difference. And what that means is that the iron or the metal or the steel or whatever your pot is made out of doesn't take as much heat per mass unit for the temperature to raise as water does. And God actually did that for a reason, because water has, of all the substances I'm aware of, it has the highest heat capacity of anything that I know of. And the reason for that is because we have a lot of life on earth that lives in water. And so if the water was able to change temperature very, very rapidly, that could be dangerous for many of the creatures that live in water. You're probably aware that in the spring, again, depending on where you live, in the spring of the year, when people maybe would start thinking about going swimming at the beginning of the summer, the water stays cold as far as swimming temperature for a very, very long time until you've had enough long days to warm that water up so that it's actually maybe more comfortable to swim in. The water stays cold. And even in the fall of the year, once the air temperature starts to really cool off, the water in a swimming pool or in a lake tends to stay warm for quite a while, even though the air temperature has started to drop. If you live close to a big lake, you'll notice that even though the air temperature may be below freezing, the lake still is not frozen, and it takes a long time for that lake to freeze to the point so that the water's thick enough, the ice is thick enough that you can actually walk on it. And so that's something that our Creator has put into the properties of the water that He made in order to protect the creatures that live there. So all that has to do with specific heat. And so in today's lesson, we're going to work on how to figure out the amount of heat that is transferred due to the specific heat of a particular substance. And we have two equations that we're going to use for that. The first one is Q equals mc delta T, where Q is the amount of heat. It could be in calories, like we talked about in the first video. Generally, those specific heat capacities are given in joules, and so normally we're going to use joules for heat. Mass, C is specific heat, and delta T is change in temperature. T stands for temperature, but we're talking about a change in temperature. So what we're looking at is a flow of heat, so the temperature is either going to go up or it's going to go down. In order to measure this heat flow. Remember, we defined in the very first video that that heat is a flow of energy, and so in order to measure a flow, there's going to have to be a change in temperature. Delta T, means change in, and if you happen to take physics later on, you'll see that you use delta a lot because we're going to measure the change in lots of different things. Here it happens to be a change in temperature. When you calculate a change in temperature, you want to make sure that you take the final temperature, which I classify as T sub F, and subtract the initial temperature from that. You want to make sure that you don't get those backwards. The final temperature has to be first in the subtraction problem because that's where it ends up. Okay? So, if a substance actually loses heat, this number is going to be negative. And that's okay, because if it drops in temperature, that means you're going to have a loss of heat. So let's kind of summarize what happens here. If my temperature goes down, okay, so something is cooling off, what that means is that my delta T is going to be negative. And so that also means that when I plug that into this equation up here, if this number is negative, mass and specific heat are always going to be positive. So that means my Q is going to be negative. So what that means is that heat has been lost from that particular object. On the other hand, if the temperature goes up, that means my delta T is going to be positive, and that means my Q is going to be positive, and that means that heat will have been gained by that particular object. Okay, so the signs here are very, very important, so you need to make sure that you're subtracting those temperatures in the correct order. So let's do a couple of sample problems so that you can understand how this works. One thing I do want to point out is that if you choose to, you can actually combine these two equations together. If this confuses you, you don't have to do it this way, but what you can do is you can say Q equals MC and then plug in TF minus T sub I and plug it in like this. All I did is take this equation and plug it in for the delta T that was over here and make this equation. Again, if that confuses you, you don't have to use it. And if you're going to do this, you need to make sure that you do proper order of operations when you solve the problem so that you don't end up multiplying by something you shouldn't be multiplying by. You do have parentheses on your scientific calculator, and you can type those in and use them if you so choose to. But again, that's optional, and you don't have to do it that way. So let's look at the sample problems that I gave you. The first sample problem says, how much heat did a 2.2 kilogram piece of glass lose if it cooled from 75 degrees to 61 degrees Celsius? The specific heat of glass is 0.840 joules per gram per degree Celsius. Okay, so if it's asking about the amount of heat that was lost, that should tell me, first of all, if heat is being lost, what should be the sign on the Q? Well, if heat's lost, the sign on delta Q should be negative, and so we need to be watching for that as we're working through this problem. So if I'm using Q equals MC delta T, notice that the specific heat that they give you is joules per gram, and so that means in order for my units to cancel, I've got to convert this mass in kilograms that they've given me to mass in grams. So whenever you take kilograms to grams, you just have to make sure that you're going to multiply by 1,000. So in this particular problem, my mass of 2.2 kilograms is going to be 2,200 grams. The specific heat they gave me is 0.840 joules per gram per degree Celsius. And the change in temperature went from 75 to 61. So that means it ended up at 61. So I've got to take 61 degrees minus the 75 degrees, okay? If you do this piece first, 61 minus 75 gives me a negative 14 degrees. Okay, so like I said, it has lost heat, so this is a negative delta T, and since I have a negative number over here, that's going to give me a negative Q, and to the proper number of significant figures, you'll notice that this has 2, this has 3, this has 2, so my final answer can only have 2, so my final answer is a negative 26,000 joules. Okay? So there's the first problem. We do have a second one here that we can work as well. This time it says, what was the initial temperature of a 5.56 kilogram piece of iron that received 16,500 joules of energy? Its final temperature was 65.5 degrees Celsius, and the specific heat is 0.444 joules per gram per degree Celsius. Okay, so let's get rid of this so I can figure out which direction I need to go here. All right, so it says I have a the first number I have is a 5.56 kilogram piece of iron. Well, again, because the specific heat is given with grams, I've got to convert kilograms to grams. So my mass is going to be 5,560 grams. Okay. Then it says it received 16,500 joules of energy. Well, if it received that, then that means it gained energy, so that my Q is going to be positive. So I have 16,500 joules of energy over here. The specific heat is 0.444 joules per gram per degree Celsius. And I'm going to solve for delta T. Okay, so you're going to take 16,500 and divide it by both of those numbers. And so then your delta T ends up being 6.68 degrees Celsius. I can use 3 significant figures because I have that in all of those up here. Okay, now recall that delta T is T sub F minus T sub I. And so I have to have a change in temperature of this amount. So if this is T sub F minus T sub I, the problem tells me what its final temperature was. So its final temperature was 65.5 degrees. I don't know what the initial temperature was, but I know that the change in temperature is 6.68 degrees Celsius. Okay, so watch your negative signs when you do a problem like this. What I would do is I would move this T sub I to the other side, add T sub I to both sides, so you're going to have T sub I plus 6.68 equals 65.5 degrees. And then I would subtract the 6.68 from both sides, because if you're not careful, you're going to end up doing this in the wrong order. So you have 65.5 minus 6.68, and that will give you an initial temperature of 58.8. We're subtracting, and so significant figures rule says this is in the tenths place, this is in the hundredths place. So that means that my final answer can't have a digit after the tenths place. So the initial temperature was 58.8 degrees. Now let's make sure that makes sense. If it gained heat, the temperature should have gone up. Well, if it started out at 58.8 and ended at 65.5, that does indeed mean that the temperature went up. So everything seems to fit there according to what the problem told us. So you will get lots of practice today in your homework assignment with these kinds of specific heat problems.